All right, well, last week we discussed the NumPy n-dimensional array container data structure type. And this week we're going to introduce pandas, which provides a couple of very useful data types built on top of NumPy. The first one is the series, which is a one-dimensional sequence of values. And a little later we'll get to what are called data frames, which are a spreadsheet-like collection of values in which the columns can have different data types, unlike in a NumPy ND array where all of the values are the same data type. Okay, so a series is a collection or a sequence of values which have labels associated with them. And those labels are used to index into the series. Now, in order to use pandas, I have to import pandas as PD to follow the usual naming conventions. And we're also going to be using some NumPy facilities in this material. It's taking pandas a while to load. Come on, come on. There we go. Thought my machine was faster than that. Okay. So let's also import NumPy as NP. Okay. So notice that was like instantaneous. So I said that pandas is built on top of NumPy. When I said import pandas as PD, that probably also inherently imported NumPy as well. All right. So to create a series, I'm going to call this series object S1. We use the series construction function in pandas, pd.series, with some iterable. So here I've got a list of integer values. And when I ask to see S1, I see not only those integer values, but I also see the default index labels that the series construction function creates for those. Notice also that I see the data type of these values. Unlike NumPy, which created int32 values by default when I put integers into an ND array, here I'm getting 64-bit integers in my series, which contains a much wider range of values, roughly between plus or minus 9 quintillion as opposed to plus or minus 2 billion in the case of an int32. All right, I can access the items within this series. Whoops, I'm jumping the gun here, so let me skip ahead here for a moment. I can access items within a series by using these index labels, just like I can access items within a list. So S1 sub 0 is the initial item, S1 sub 1 is the first item. What's different about a series versus a list is that I can have different index labels rather than just integers 0 through n-1 if there are n values in there. I can in fact find out what the current values and what the current index is of my series. In this case, when I ask for S1's values, I get basically the same thing that I got when I just displayed S1. I get told that the values are 3, 5, 2, and 4, and the data type is int64. Now for the index, rather than having a list of these values 0 through 3, internally within a series there's a special iterable function, range index, similar to the top level range function. And my series of indexes for S1, 0, 1, 2, 3, is described by having a start value of 0, a stop of 4, and a step of 1. So stop is one past the end of the list of values that are going to be used for the indexes. The benefit of using a range index to keep track of that index, of course, is that I don't have to use extra memory to store all those values. If I had created a series of 1,000,000 values, it's a lot more convenient to store a range index description, start 0, stop 1,000,000, step 1, as opposed to having a list of 1,000,000 subscripts from 0 up through 1 less than 1,000,000. All right, if I want an index of my own design, in this case I'm using an index of strings, I can do that by specifying the index keyword parameter. So here I'm saying S2 gets pd.series. Once again, I'm using a list to specify the initial values that I want in the series. But this time I'm specifying my own index rather than accepting the default 0, 1, 2, 3. Okay, so the first index is going to be the string A, then X, then the string capital C. And I'm not restricted to just letters. I can use any strings that I want. So here I'm using a punctuation mark, question mark for my last index. I can access items in S2 by using ordinary integer subscripts. That works. Okay, so the first item in S2 is a 4. But I can also use the named index labels as well. And so if I say S2 sub string question mark, I get the 5, which is the item in there that the question mark index is associated with. Okay? All right, so when you create a series, you will get an integer index by default, just starting from 0 up through 1 less than the number of values in your series. But you can specify an alternate index if you wish. Now, a dictionary, recall, consists of keys associated with values. And it turns out we can trivially create a series from a dictionary because the keys, which are required to be unique in a dictionary, will be used as the index labels, and the values associated with those keys will become the values within the series. All right, so here I've got, and I'm going to copy and paste this rather than type it in manually. Here I've got a dictionary describing prices for 3 stocks. All right, dictionary is named D1. Pardon me. X is the ticker symbol for U.S. Steel, which is a locally headquartered company within Pittsburgh. It used to be what is now the UPMC building downtown used to be the U.S. Steel building. And we've got a price here of 123.2. I have no idea whether that's anywhere remotely close to a valid price for U.S. Steel. I've also got Apple and Cisco with, again, prices that are just kind of made up from thin air. And if I create a series named S3 by specifying my dictionary as the argument, I will get the ticker symbols as keys and the prices as values associated with those keys. Just like in NumPy, these floating point values are stored as full of 64 format, so 64-bit floating point format. I can use the same style of notation to discover whether a value is in a series that I could with a dictionary. In other words, if I say X in D1, I get true because X is in the dictionary. If I say GS in D1, all right, well, I tried to look up Goldman Sachs in my dictionary and it doesn't exist. Same thing is true for the series. If I ask whether Apple is in S3, I get told true, and if I ask whether ExxonMobil is in S3, that's not. We can do arithmetic with series using sort of vector style arithmetic in much the way that we did for ND arrays. So arithmetic is not doing concatenation and repetition as it's used for lists. We can also use slicing and indexing within series, again, very much the same way that we do with ND arrays. All right, so here's my series S1 that I created with the default index and these values 3, 5, 2, 4. If I multiply S1 by a scalar, here I'm saying S1 times gets 2. This is an integer multiplication into integer values. The results will therefore be integers, and I'm simply going to double each of the values within this series S1. All right, so S1 originally contained 3, 5, 2, 4. Now it contains 6, 10, 4, 8. Division always yields a float. So if I create a new series S4 by taking S1 and dividing by a scalar 2, S4 is going to be the floating point representations of the original values that I stored into S1. So I've got 3.0, 5.0, 2.0, and so on. If I do floor division, as we're doing here in this second example, I can convert the okay, my mistake. I was going to say S4. So S1 contains integers. If I want to get back the original integer values that were in S1, I can do a floor division. So instead of just plain division, which would give me floats, I do a floor division by an integer, and that gets me back to my original integer values, 3, 5, 2, 4. Addition, instead of doing concatenation, as in lists, we'll do a vector-like addition. So I get 6, 10, 4, 8. Now, I don't have any assignment operator going on there, so this does not change the value of S1. It just created and returned a series that was the sum of 2 copies of S1. I can, using a pandas series, invoke vectorized NumPy mathematical functions. So if I say np.square root of S1, that gets me back a series, which is the square roots of all those values, 3, 5, 2, 4. And I can do np.natural log of S1 and np.cosine of S1 and all these, all these usual arithmetic functions, vectorized computations from the NumPy module. All right, S1 sub 2 gives me just one item sub 2, but S1 sub colon 2 is a slice, behaves the same way as in an ND array. I get all of the items up to but not including item sub 2, so that's item sub 0 and item sub 1. Likewise, if I say 1 colon, actually we're using S3 for that example, so let's remind ourselves what S3 contains. S3 is the stock tickers and prices. So if I say S3 sub 1 colon, I'm going to get Apple and Cisco. Remember that the indexes in, pardon me, let me back up a moment. Remember that the keys in a dictionary are in the order that the keys were specified in when the dictionary was created. When I create a series from a dictionary, those indexes are in the same order as the keys were. They're not alphabetized automatically. In previous versions of Python, they would have been they would have been alphabetically automated. No, they would have been automatically alphabetized. But that's not true in Python 3.7. So I'm going to get Apple and Cisco from this slice. Now, if I use the named labels, I get a slightly different behavior than what we're familiar with. If I say S3 sub Apple colon Cisco, from previous experience looking at this slice, you would expect, oh, that means starting from Apple and going up to but not including Cisco. But actually, if you're using a string as a label, then you are including that final label as well as the initial label. So this is a sort of abrupt change in behavior relative to ordinary integer subscripts. So S3 sub Apple colon Cisco does mean starting from Apple and going up to and including Cisco in my slice. Now, let's suppose that we have two different series that don't have exactly the same indexes. All right, here I've got S1 containing indexes 0, 1, 2, 3, and I'm creating S6 as a pandas series containing the integer values 3, 7, and 1. But this time, as my index, I am going to use integer subscripts, but I'm not going to use the default 0, 1, and 2. Instead, I'm going to use the range index 2, 5, meaning from 2 up to but not including 5. So the indexes are going to be integers, and they're going to be 2, 3, 4, as opposed to the default 0, 1, 2. All right, so we can see that S1 has integer indexes, S6 has integer indexes. There's some overlap. Both of them have indexes of 2 and 3. Whoops. Changed my window size there. All right. So both of these series have indexes 2 and 3, but S1 has 0 and 1, and S6 has 4. It turns out if I add these guys together, here I'm going to create a new series, S1P6. That stands for S1 plus S6. So S1P6 gets S1 plus S6. Now, in the case where the indexes are the same between these two series, the values associated with those indexes are just added together. But in the case where one series has an index that the other series does not have, what we get instead of a sum is this not a number special value. All right, and so if we look at S1P6, we see that, okay, S1 had these two indexes, well, still has, these two indexes 0 and 1. Those indexes don't exist in S6, so my sum produced not a number in the resulting series for indexes 0 and 1. Likewise, S6 has an index 4 that S1 doesn't have, so likewise there, for the index 4, I have not a number. So the only two values that are numbers, as opposed to not a numbers, are for the indexes that are the same between the two series. Index 2, I have 2 plus 3 is a 5, and index 3, I have 4 plus 7 is 11. Now, why are these floating point? Is a worthy question. It turns out that not a number is represented as floating point. All possible patterns of bits that will fit into a 64-bit integer represent valid integer values. So if we do a sum and we get not a number, there's a special floating point bit pattern that represents not a number. And consequently, if we have converted one value in our sum to a floating point, the upcasting rule means that all of the values in this series get converted to floating point, in this case float 64. All right. I can test using the isNull function in pandas which of the values in the series are not a number. And what I get is a Boolean vector, true, true, false, false, true. I get true for all the not a numbers and false for the valid numbers. Now, as an alternative, you can also test whether is nah S1 P6 nah for not available or not applicable or whatever does exactly the same thing as is null. And then the reverse of those functions are not null and not nah. So if I want to get a Boolean index of the values that are not null in S1P6, I say pd.notNull S1P6, and here I have true. It probably won't startle you too much to realize that within S1P6 I can use that Boolean index to get the subset of indexes where the values, whoops, not null, not, okay. I can use that Boolean index to get just the indexes where there are valid numbers. Okay, so I've got the value with with index 2 and the value with index 3 in my result from that Boolean index. Okay. Now, a data frame is the other important data structure provided by pandas, and it is a spreadsheet-like data structure. It has n rows, and the columns are named, and the columns can have different data types. If you're familiar at all with the R language, you may be acquainted with the data frame structure in R, and the Wes McKinney, who developed pandas, was a big fan of R, or is a big fan of R, and liked having the data frame structure available in the Python work that he was doing. So he actually originated the data frame data structure type in Python to emulate the R data frame. As with an ordinary series, it's easy to build a data frame from a dictionary. The distinction is, instead of having the label associated with a single value as we would with a series, now we're going to have the label associated with an iterable on some number of values. And it's important when I create a data frame that all of the columns have the same number of rows. That is, all of the iterables associated with the column labels have to be of the same length. In this particular case, and I'm going to copy and paste this, I'm certainly not going to type this in by hand, I have this dictionary D2 in which the first key is the ticker symbol for some stock. Some of these are just made up. The second key specifies whether the CEO of the company has recently bought stock. I may or may not have mentioned that one of the other hats that I wear is teaching for the MS of Computational Finance program at the Tepper School, where we're all concerned about stocks and bonds and interest rates and exchange rates between different kinds of currencies, and et cetera, et cetera. And one of the things that analysts often like to know in order to estimate whether the value of a stock is likely to increase is whether the CEO has been buying the stock or not recently. In this case, the CEO has been buying the stock for a company with ticker A, but has not been buying the stock for the companies with tickers B, X, and G. By the way, I will give you a hint. It turns out that CEOs are not good judges of the short to medium term prospects of their company's stocks. And so knowing whether the CEO is buying the stock turns out not to help you much if you're trying to make a decision yourself as to whether to buy the stock or not. But it turns out that the chief financial officer is a much better indicator. So in addition to checking whether the CEO is buying the stock, we really ought to be checking whether the CFO is buying the stock. If the CFO is buying the stock, or conversely selling the stock, not buying the stock, that's a better indicator as to whether the price of the stock is likely to go up or down in the medium future. Okay, the third column here, which is also something that investors like to know, is what is the percentage return on the stock, let's say over the course of the last year. So here we've got 11.1 minus 4.4, so the value of this stock actually declined, and 12% and 23.4%. If I take D2 and build from that this data frame F1, the data frame shows me that information in a nice tabular form if I ask for a default display. And notice that the data frame creates these default row labels 0 through 3. I can, if I wish, specify alternate row labels, but since the ticker is actually one of the columns in this data frame, it would be redundant to use the ticker as my row labels for this particular data frame. All right. Now, in my data frame, I can use a row label, I can use a column name as a subscript to get the vector, the series, containing that column of values. All right, so F1 sub CEO by, and the name is a string, so I'm specifying the name as a string, gets me back that particular column. Similarly, F1 sub ticker would get me back the column of ticker symbols. Notice that when I ask for that series of the CEO by column, or when I ask for the series of the ticker column, in addition to being told the data type of that series, I'm also given a name for the series. And the name is simply the column name. Previously, when I created the series S1, I was told the data type for the series, but this series does not have an internal name associated with it. Now, it does have the variable name S1 referring to it, but it doesn't have an internal name. I can create an internal name for a series by just saying a reference to the series and then .name and assigning some string. So I am S1. Now, I typed the double quote by accident, but who cares? And now if I display S1, I get told, all right, this series is named IMS1. All right, so that's internal within the series. If I were to come along and say S1 R for S1 reference, now S1R refers to the same object as S1, and so if I display S1R, it is the same series with its internal name IMS1. All right, let's display F1 again. So here we've got the ticker column, the CEO BA column, and the return percent column. If the column name does not have any special characters in it, that is, if the column name would be a valid Python identifier, you can actually just say F1 dot and the column name as an abbreviation for saying F1 sub and the column name in quotes. All right, so in the case of CEO BY, this string CEO BY does follow the rules for a Python identifier. That is, the first character is a letter or an underscore, and subsequent characters are letters or underscores or digits. Consequently, I can just say .CEO BY as an abbreviation for sub CEO BY and using the quotes. That won't work for return percent, however, because the percent sign is the modulus operator. And so if I attempt to say F1 sub, F1 dot return underscore percent, now Python is going to yell at me because it doesn't like that percent symbol in the name. I do have to use the sub notation and specify return percent as a string to get that particular column displayed as a series. Okay, so that's columns. You say the data frame and then either dot column name, if the column name is a valid identifier, or sub column name in quotes for any column. Now, to get a row, I guess I would have to interview I've been doing a bunch of R programming lately, and so the only name that pops into my head is Hadley Wickham, who is the R guy. No, this is Wes McKinney. Wes McKinney. I would have to interview Wes McKinney to find out what he was thinking about this .loc. But if I want to get a particular row from F1, I say F1.loc and then an index. So F1.loc2 gives me a series representing the row. Now, the values in a series have to all be of the same data type, And in this case, what we have are a string and a Boolean and a float. So in order to have these be represented as the same data type, the upcasting results in all of these things being called object. Okay, so these guys are objects. And we can individually test what the individual data types of these are. In other words, I can say f1.loc sub2. That's a series. So sub1 is going to be the x. No. Okay, I've been doing too much R lately, and indexes go from 1 to n instead of 0 to n minus 1. I meant to say f1.loc2 sub 0, and that's a string. And we can confirm that by asking for the type of it. Okay, so that's a stir. f1.loc sub 2 sub 1 is a bool, and the return percent is a float, although because the fraction part is 0, I'm not seeing a decimal point there. But let's just confirm that just to... So the percentage return is a float. All right? Specifically a NumPy float 64, but that's the same thing as a Python float in terms of how it's represented in memory. Okay, so we've seen how to retrieve a column as a series by specifying the column name, either as a subscript or following the dot if the column name is a valid identifier. And we've also seen how to access a row by using the .loc notation and then an index in square brackets. To access an individual cell, let's suppose that we wanted to access this particular cell of the data frame. Well, I can either access the column and then access an individual cell within the column, or I can access the row and then access an individual value within the row. Or another way I can use .loc is to specify the row and a comma symbol and the column. All right, so all three of these approaches are going to work. I can say f1 sub CEO by. That gets me a column, and within that column, sub 2 is going to be the this cell whose value is false. Or I can say f1.loc sub 2 sub CEO by, accessing the cell by using the row first followed by the column. Or, as opposed to using two subscripts, I can use two separate subscripts, if you will. In other words, instead of getting the row and then from within the row getting the cell, I can ask for row, comma, column all at once in my square brackets. Okay, so we introduced the idea of a data frame. We introduced the idea of constructing a data frame from a dictionary. There are other ways that you can construct data frames as well. And then we took a look at how you can access individual columns, individual rows, and individual cells within the data frame. Now, if you want to add another column to the data frame, this is easy to do. You use a syntax that's very similar to how you would add a column, that is, add a key to a dictionary. You say, all right, here's F1. It has ticker, CEO by, and return percent. let me say F1 sub P/E. That will create a new column, assuming, now if I just stop there, if I say F1 sub PE, I get an error message, because there, oh, woo, I get a I get a huge error message. I get a big red angry error message because there is no such column, and in fact, eventually, Python gets around to reporting this key error. All right. But if I say F1 sub PE and then do an assignment to that column, 20.5 here is the scalar example that we're using, then that column will be created just as the key would be created in a dictionary. And by assigning a scalar to the column, that has the effect of every cell in that column all being filled in with the same value. P/E, by the way, is what's called the price to earnings ratio. It specifies the amount of money that you have to pay for a share divided by the amount of earnings that the company reports each year for on a per share basis. 20.5 is considered to be on the high side. Usually investors are interested in PE ratios down in the 10, 12, 14 kind of range. If the PE ratio is too high, well, let's look at it this way. What does 20.5 mean? What 20.5 means is that if I pay, let's say $100 for a share, and every year the company just sends me a check for my share of the earnings. That doesn't actually happen, but it would be a swell thing if it did. If the earnings don't increase over time, it's going to take me 20.5 years to get my $100 back that I spent on that share of stock. So 20.5 years is a long time to wait to get paid back for the $100 that you spent on the share. Okay, now in the tech community, where tech stocks often grow at a very rapid pace and also unfortunately fail at a very rapid rate, often investors think, well, the company is growing so fast that a PE ratio today of 20.5 is not really that frightening, because 5 years from now, the company is going to have 5 times as much earnings, and so the PE ratio will be the equivalent of like 4. So even though the PE ratio today claims to be is 20.5, I just take last year's earnings and divide it into the stock price, and I get 20.5. So even though today's PE ratio is 20.5, if the company grows rapidly enough, I might get paid back within, just 3 or 4 years. Okay, so that is a risk, but it's a risk for some companies that investors are willing to take. Well, all right, enough babbling. Let's create this column PE, and PE is going to be 20.5 for every one of these stocks, because I did a scalar assignment. If instead I do an iterable assignment, that iterable has to have exactly the same number of values in it that there are rows in the data frame. So in this case, I'm saying F1 sub peg ratio gets. And let me copy and paste that vector so I don't make silly mistakes typing it in by hand. Whoop. All right, so now each of those individual values is going to become the value of the corresponding row in F1. Okay, so I've just added another column to this. Now, what is the PEG ratio? Well, the PEG ratio is the price earnings to growth ratio. And so what this is telling me is, okay, the PE ratio for ticker A may be 20.5, but it's growing at a fast enough rate that if I take the price earnings ratio and divide it by no, I got that backwards. If I take the growth rate and divide that by the PE ratio, I get a 1.7. All right, so any value greater than 1 is good here because it means that the company is growing at a pretty good pace. 0.9, 1.1, those are not very impressive. Actually, 1.7 and 2.2 are not wildly impressive, but if this was the entire universe of stocks that I could invest in, and all of these stocks had a PE ratio of 20.5, then not knowing anything else, I would be happiest probably investing in this company X because that one's growing at the fastest rate based on its current PE ratio. Okie doke. So that's how you add a column. You just say DataFrame variable sub column name equals, and then either a scalar or an iterable that has the correct number of values in it corresponding to the number of rows in the data frame. If you decide you want to get rid of a column, all right, we've added a column, now we need to know how to get rid of a column. You do that with the del command or keyword. So del and then F1 sub P/E will simply eliminate that entire column. And now F1 no longer has that PE column in it. Adding a row is similar to adding a column. We have to remember to use the loc notation before our subscript. So currently F1 has 4 rows, row sub 0 up through row sub 3. If I want to add a row sub 4, I almost blew it. I've got to say F1.loc sub 4. And then here, you typically can't get away with a scalar because the data types of the different columns are different from each other very often. And so here I'm going to add a string Z as my ticker, the Boolean true to indicate that the CEO is currently buying the stock. And then I'll have a return percentage of 8.2% and a PEG ratio of 1.3. And there we are. So I have now successfully added row 4. You need to be cautious about adding rows for a couple of different reasons. To illustrate how you can go wrong with adding rows, let me make a copy of F1 called F1C. And F1C is an independent copy of F1. It has rows labeled 0, 1, 2, 3, 4. Now, just because the row labels were initially specified as integers, in fact, if I ask for F1C.index, it was a range index initially, but since I added 4 manually, it's been converted into an N64 index here. If I make the mistake of adding a row, let's suppose I meant to add row number 5, but I typed 0.5 by accident. Well, 0.5 is a valid row index, and if I make a different dumb mistake here and assign a scalar value 12, since the columns in the current data frame have different data types, assigning a scalar value to this new row is going to do upcasting on all of the columns. All right, so this is really going to mess me up. I have accidentally used a floating point value as an index. That means all of these integer indexes are going to be upcast to floats. Also, I've assigned a scalar 12 to all of the columns, so the Booleans are all going to be upcast to integers, and 12 here is going to be, for the ticker, is going to be converted to a string. So here's F1C now. All right, and instead of having true and false for my CEO by, I now have ones and zeros with a 12 at the bottom, and this is a problem. All right, so there is no Control Z that I can press that will undo this dumb mistake that I made. I can get rid of a row. Now, it would be nice if things were consistent and I could say del F1C dot loc sub dot 5, but no, that would be too simple if things were consistent and I could get rid of a row the same way that I get rid of a column. No, what I have to do is I have to say F1C dot drop and then give my label. All right, so this will eliminate that row that has the label of 0.5. However, whoops, well, there's two howevers here. First of all, if I use drop this way, that doesn't actually modify F1C. What it does is it creates a copy of F1C with that row 0.5 eliminated. So F1C has not been changed here. F1C dot drop of 0.5 creates and returns a copy of F1C with that row dropped. If I therefore wanted to change F1C to refer to this new data frame in which that row has been dropped, I can use an assignment. That's one way I can do things. Turns out there's also an option I can use to cause the dropping to be done in place on the existing data frame. But in any case, that's not what I'm trying to warn you about here. Although I did drop that row with that bogus index, that does not magically undo the upcasting that occurred. All right, so once you upcast your data, you're kind of stuck. So don't do that. And as you're developing code manipulating data frames, you're going to want to be careful and go step by step and display your intermediate results to make sure that you're not accidentally corrupting the contents of your data frames. All right, so now we know how to create a data frame. We know how to access a column or a row or a cell. We know how to add and remove columns, and we know how to add and remove rows. In the next section, we're going to take a look at slicing and indexing within data frames.